Hello. My name is Mengucho from Kyushu Institute of Technology, Japan. Today, I like to talk about a new initiative to standardize electrical interface of CubeSat. First, I ask you a question. Are CubeSats delivered fast? Has been said that the advantage of CubeSats is low cost and fast delivery. Low cost is probably true. Some can build a CubeSat with $30,000 or less if it is designed carefully and manufactured with good hands. But are we making CubeSats fast? This graph shows the statistics of delivery time of 1 to 10 kilograms satellites since 2003, which is mostly CubeSats. To correct the bias in the statistics, we excluded Spire and Planet. The delivery time is from the project kickoff to the launch. You can see quite a few satellites takes more than 2 years until they get to the launch site. This is more true for university satellite. More than 2/3 of the university satellites are taking more than 2 years. Private companies are doing relatively good as the longer time means the more cost. Still, 1/3 of the satellites is taking more than 2 years. From this statistics, we can say that CubeSats are not necessarily delivered fast. Delivering the satellite value fast to the end users/customers/stakeholders is important. For commercial programs, more time means more salary. For small satellites, salary, personnel, is the biggest expenditure. It may also lead to the loss of business opportunities by losing the competition with other solutions by satellites, aerial, terrestrial applications. Even for university programs, fast delivery is important. First, because the mission success rate decreases. Second, there is still academic competition. Being the first to do in-orbit demonstration is important. We now look at the effects of interface incompatibility. It does not directly affect the satellite reliability, because the interface incompatibility should have been solved during the system integration before launch. In principle, not many issues should remain unsolved when the satellite is launched. But the interface incompatibility leads to delay in the schedule, because we need more time to solve the interface incompatibility issue. We do many try and errors. Then, there will be less time to spend in other verification processes, such as deployment, software, communication, thermal, others. Then the mission success rate will decrease. Also, the delivery time gets longer. Nowadays, we can build a CubeSat by buying all the components in internet, thanks to international trading of CubeSat components. But combining components from various vendors is risky. By combining EPS from a company A, OBC from a company B, and COM from a company C does not make a nice system. Indeed, many CubeSat developers now tend to buy components from a single vendor. PC-104 has been the de facto standard of CubeSat interface. There are, however, many problems. First of all, because it has 104 pins, there is too much flexibility that leads to interface incompatibility. There are other problems such as difficulty of assembly and disassembly processes. There has been a survey regarding the PC-104 interface in 2014. Many people who used PC-104 style felt the connectors are too big and pin assignment is too flexible. Also, when we consider interface of CubeSat, we should think about the mass production. Now, small satellites are entering into the era of mass production. It is more true for CubeSats as the unit price and the launch prices are much cheaper than the other classes of small satellites. To do mass production, satellite assembly, integration, and testing can be done in parallel by making the satellite harnessless, adopting batch production and batch testing. To do so, the satellite interface must be designed from the beginning to adopt rapid and uniform assembly. This is a picture when my students produced 5 1U CubeSats simultaneously. At each table, 2 or 3 students assembled a satellite. In terms of quality control, it is a nightmare considering the poor hand skill of the students. To assure the uniform quality as much as possible, this type of harnessless design was adopted from the beginning. To do so, the interface of each PCB components must be defined very well. So, the interface is very important for CubeSat. Therefore, I started a new project to standardize the interface. The project is funded by the Japanese government. Its goal is to make an ISO standard to define electrical interface of CubeSat. My target is to have the standard published in 2024. Let me briefly explain what standard is because some of the audience may really hate the word which is against freedom. Standard is not a regulation nor a law. Law is more serious and compulsory. If you violate a law, you may go to a jail. Regulation is a little bit relaxed. If you violate a regulation, you may be punished, but not physically. Regarding standard, it is up to you whether you follow or not. If a contract says follow ISO, then you have to comply. Otherwise, you may be sanctioned financially, but not physically. Standard makes the life better and easier. It promotes international trade and collaboration. It can also serve as the basis of regulation and law. This is one example showing benefits of standard. Before the ship cargo container was standardized, the work at ports was really mess and very, very labor intensive. Nowadays, you don't see people at the container ports, revolutionizing the cargo transport by ships. Another example is, as you know, CubeSat standard. It is basically the interface standard between the satellite and POD. It is now an international standard with a number of 17,770. There are already some ISO standard related to small satellites, which include CubeSat. ISO 19683 is about testing. ISO TS 20991 is about the minimum requirements for the satellites. The benefits of the CubeSat interface standard are the following. It can shorten the time required for design, development, assembly, integration, and testing. It can promote mass production. It can assure component compatibility, leading to promotion of international trade of CubeSat components and international collaboration. In the standardization project, we do the following 5 things. Making and revising the standard draft. Coordinating with ISO/TC20/SC14. Investigating compatibilities among CubeSat components in the market. Collecting inputs from the worldwide experts and stakeholders through IAA, International Academy of Astronautics. Organizing international workshops to exchange information and to discuss the standard. The project proceeds in parallel with IAA Study Group 4.26. I used a similar method when I led the activity to make the testing standards and the requirement standard. There is an official website called LeanSat. In this website, you can access to all the previous meeting minutes, presentation, and others. We have a mailing list to distribute the information. If you want to join, please send me an email to me. In 2019, we had several meetings, including the side meeting during the Small Satellite Conference. The biggest meeting was the International Workshop on Lean Satellite that was held in Tokyo for 2 days in December. There were total 88 people, including 33 from abroad. In the workshop, we discussed what should be included in the standard. Considering the latest trend of CubeSat platform, rather than sales of single components, we realized that interface between platform, satellite bus, and mission payload is also important. Many vendors now provide a CubeSat platform that makes the volume for mission payloads available, so that those who want a quick demonstration in orbit can build and launch a satellite quickly without worrying to make a satellite. There are also documentation to describe the interfaces. Because many developers first look at the documents before they decide which one to buy from internet. The information in the datasheet must cover the common items, so that the satellite developers can compare the products and check the compatibility among the components, and with the components they are building by themselves. Around the time of the December workshop, I circulated some questionnaires to do a survey on CubeSat interface. 50 people already answered. Among them, there were 21 developers and 9 vendors. You can see more than 50% of the developers use PC104 type architecture. Also, many buy components from vendors. This shows what they bought. The developers tend to buy COM, as it requires a high skill in analog microwave circuit. Also, more than 1/3 bought from a single vendor. Still, more than one half bought components from multiple vendors, which is not really a good practice. The reason why the developer chose the single vendor solution or multiple vendors solution are listed here. The requirement on performance and functionality dictates and make them to buy from multiple vendors. 3 chose the single vendor solution to avoid any interface incompatibility. I also asked about the harness. There is still a long way to go to a harness-free CubeSats. The major reason is solar panel, payload bus interface, umbilical, and others. I can understand to connect with something at the external panel's harness may become necessary. But with careful design, we can remove the harness even from the interface between the external panel and the internal units. I asked about the digital interface. You can see that the developers favor simple serial communication digital interface. But in future, they tend to favor CAN and Ethernet to adopt to more complexity and high-speed requirements. On the other hand, vendors favor SpaceWire as the future digital interface, although many developers do not agree. I also asked about how to improve the CubeSat delivery time. Many people pointed out interface. It is interesting to see that many developers also say that the software. This is another research item carried out in the project. We study how really difficult it is to combine CubeSat components from different vendors. To be honest, at QTech, we do not use PC-104 architecture, and we have our own backplane-style architecture. Therefore, we have had no experience of PC-104. We wanted to know the complaint made by people about PC-104 is true or not. To study, we selected 3 vendors. Onboard computer, OBC, from ISIS. UHF transceiver, COM, from Clyde Space. Electrical power system, EPS, with battery from GomSpace. Probably, this combination is not realistic as many will buy from a single vendor. But, we tried to combine the 3 to see whether they can work nicely. The result is that it is not so easy. First of all, the technical documents need to be improved and updated. Many information is hidden in the document or outdated. We managed to integrate OBC and COM, though we still need to improve the OBC software to fully utilize the COM capability. Integration between OBC and EPS was very difficult. Simple analog integration was okay. The EPS could provide a power to OBC without any problem. But, once OBC tried to communication with a microprocessor inside EPS, it became very difficult. Conclusion. A new project to standardize the CubeSat electrical interface has started. This project is open to anybody who are involved in CubeSats. We not only write a standard, but also do research works. The results will be shared with the project participants. In the presentation, I did not touch any of the standard draft. The contents of standard draft will be discussed more in the side meeting. Please check the conference schedule and see there.